Welcome, everybody, to the first Heidelberg Joint Astronomical Colloquium of the semester. I'm very happy to see such a lively turnout today. So there's an attendance sheet going around. That's just so we can get the snacks reimbursed. So just put your name down, and if you don't, it's okay. But so today we're very excited to have a talk from Nadine Neumayer. Nadine did her PhD actually here in Heidelberg at MPIA. And then she was an ESO fellow and then ESO staff in Garching. After that, she came back to Heidelberg, to MPIA as a group leader. And in 2020, she was selected for the Lisa Meitner Excellence Program. And today we're going to hear about all the exciting things that she's been doing the past years here in Heidelberg as part of her habilitation talk.
Thank you. Okay. Yeah, thank you, Catherine, and thanks everybody for coming. It's a real pleasure to tell you today about my work and the work of my group, about the question of how black holes get to the centers of galaxies. And I'd like to convince you that we've made a lot of progress. And actually about 10 years ago, when I arrived here, I gave a colloquium and I looked at all the stuff that I've done in between, and I'm actually quite proud of what we have achieved. So I'd like to tell you about all the progress we've made. And looking at the centers of galaxies, like the center of our Milky Way that you see here in the background, this is the nucleus of our Milky Way, what they can tell us about how black holes get to the centers of galaxies. Okay, but to bring everybody to the same page, here when we start, I'm talking about black holes today, and black holes come in a variety of masses and sizes. And here on the low mass end, we have stellar mass black holes that form at the end of the lifetime of very massive stars at around masses of more than 8 solar masses. And the very, more or less recent success and breakthrough was the detection of gravitational waves when these very massive systems merge. And actually, there was a Nobel Prize awarded to the detection of gravitational waves to Rainer Weiss, Barry Barish, and Kip Thorne in actually 2017, just right after the detection. On the other mass scale, you have the supermassive black holes with masses more than 1 million solar masses. Those live at the centers of galaxies. And while we understand how stellar mass black holes form, more or less, we understand this, we have no clue how supermassive black holes form. And this is exactly what I would like to contribute to with my research. On that side, we have detections at the centers of galaxies, as I said, and one, again, very prominent discovery or breakthrough was the image of the black hole at the center of M87. And this image been possible with a very large collaboration, the Event Horizon Telescope collaboration. And they showed with this image that M87 has a black hole, but also that it has an event horizon. So this is pretty spectacular. And then you can do a time series of these observations and see that the accretion process actually is time varying, and you take several images of the black hole. In between those, you have the Milky Way, which is the best studied supermassive black hole at the center of a galaxy. Also, this observations got a Nobel Prize. Actually, Roger Penrose, also Andrea Ghez and Reinhard Genzel shared the Nobel Prize for the detection of a massive object, compact massive object at the center of the Milky Way. And you see here more than 16-year observations of actually 20-year observations of an orbit of a star around the black hole at the galactic center. And these observations show that it has around 4 million solar masses. And these resolved observations you can only do in the closest objects, like center of our Milky Way. And you can also, with better instruments, show that there is gravitational redshift close to the when the star S2 actually goes in pericenter passage, which is a spectacular measurement to make. And you see in between the stellar mass black holes and the supermassive black holes that start around 1 million solar masses, you have this large gap in mass. And this is the so-called intermediate mass black holes that has been long been, suspected to be there. They should be there. but it was actually impossible to observe them, and we now made a big breakthrough recently. On the low mass end, the gravitational wave detections actually eat into this intermediate mass black hole gap with the detection of a merger with a product of about 140 solar masses. So we're trying to make progress from both ends. So I told you about the center of the Milky Way. I want to take you on a journey to actually measure the black hole mass at the center of the Milky Way. So when you look at the center of the Milky Way, we're sitting in the disk of the galaxy. We're looking through the disk. Oops. I'll start this again. And you see that the optical light is blocked by more than 30 magnitudes of extinction. So you don't see the light coming from the center of the Milky Way in the optical wavelength. But when we look in the near infrared or mid infrared, you start to see a cluster of stars, the nuclear cluster of the Milky Way. It comes out round about now. And inside this cluster of stars, there is a cluster of very young stars, the S star cluster. And the teams of Andrea Gese and Reinhard Genzel, they have taken pictures, individual images of the position of these stars over more than 20 years and reconstructed the orbits of the stars that go around the center of the Milky Way. And these are actually now the images put together to a movie. And you see this is the so-called S2 star, and it goes around on basically a Kepler ellipse. And it is going around the Sagittarius A star black hole, supermassive black hole at the center of the Milky Way. This type of measurement you can only do in our own galaxy because other galaxies are just too far away to resolve the individual positions of the stars. So what do you need to measure the black hole mass in other galaxies? You need a dynamical tracer for the mass because this is an indirect measurement. You want to observe the motion of stuff going around the black hole. In the galactic center, you have these resolved orbits of stars, but in other galaxies, you need very good spatial resolution to resolve the region where the black hole dominates the potential. So you can see here, this is the nuclear star cluster. The black hole sits right at the center, but the further you go away from the black hole, the more and more mass accumulates in the stars, and then the contribution from the black hole gets smaller and smaller. So in order to resolve the dynamical imprint of small black holes, you need very good spatial resolution. And then you need to put up a dynamical model for the gravitational potential that separates the stars from the black hole. And so what I did when I was just at ESO as a staff member, I put together a program to use the center of the Milky Way, observe it as if it was an external galaxy. And so we put a slit perpendicular to the galactic plane, and we drifted over the center of the galaxy observed while reading out the observations. And in 2 nights of observing time with the VLT, we put together basically an integral field unit map. So at every point here, a spexel of the binned ensemble of stars, you measure the spectra, and from those characteristic line of the CO absorption in the stellar atmospheres, you measure the position, so the line of sight velocity, but also the width of the line, which is the dispersion, the random motion of the stars. And so by doing this and having an excellent PhD student, so Anja Feldmayer-Krause actually worked on putting together those data, you get a map of the motion of the stars around the Milky Way center. And this is the central 10 by 10 parsecs roundabout. Sagittarius A star sits right here at the center, and you see the redshifted side going away from us, blue side coming towards us. So this is basically the first 2-dimensional map of the motion of stars at the center of the Milky Way. And we not only have the line of sight velocities, but we also have the velocity dispersion. And as I said, this is Anja's work, who has put all of this together. So this is the velocity dispersion map. So you see here is where Sag A star sits. You have an increase in velocity dispersion, so unresolved motion, rotation. And you can really very well resolve the sphere of influence of the black hole, which is around a parsec at the center of the galaxy. So where all this increase in velocity dispersion is where the black hole dominates the potential. And we have used models that we have also used for other galaxies, other external galaxies to measure the black hole mass. And in this case, we know the true answer, the black hole mass. So we can calibrate our models and see whether we get the right answer. So Anya did this in a later paper, 2017, with the Schwarzschild models, so orbit superposition models, where you look at the individual orbits of stars that you can have in this sort of potential. And this is the prediction of the model. And we get the black hole mass of 3 times 10 to the 6 solar masses, so a little bit lower than what the actual measurement of the result stars is. So within the uncertainties that are definitely larger than the result orbits, it's actually consistent with the truth. And so we're quite happy that we have a unique validation of the models that we also use for external galaxies. So this is great. So, but whenever you look at the black hole, whenever you look at the massive galaxy, you also find a massive black hole. And now we see that we can also trust these models that we're using. And when we measure the mass of the black hole and we measure the mass of the galaxy, it looks like those follow each other. And this is surprising. And this is work, very early work, my first paper, where we showed that the black hole correlates with the bulge mass in a galaxy. And this correlation is surprising because the black hole influences a region that is on the parsec, maybe 100 or 1,000 parsec scale, while the total galaxy is on orders of magnitude larger scale. So it does not know, the galaxy does not know about the mass of the black hole, but somehow they seem to correlate. So this close correlation maybe tells you something about the coevolution of black holes and galaxies. So they seem to grow together. So the larger the galaxy, because it forms and grows through mergers and has like in the biggest, in the M87 case, it's basically an elliptical galaxy that has had many mergers on its way to the evolution. Also, the black hole has grown through mergers and accretion. But then very interestingly, there is also a low mass end. And I think these low mass galaxies can tell us a lot about how black holes get to the centers of galaxies, because those sit at the start of the evolution. And so this has been the question that was driving my research basically for the past 10 years or so. So what is happening at the centers of these low mass galaxies, and do we find black holes there too? Okay, so black holes and galaxies kind of are correlated. And when we look at the distribution of black holes in local galaxies, this is more or less what is observed. It's a few years old now, but this is kind of the black hole distribution in the local universe. But if every galaxy in the local universe would have a black hole, this is what you would expect. So you would expect many black holes in these low mass galaxies at low masses. And the question is, do those exist, or is this that we haven't seen them? Is this just the detection threshold? And I will hopefully convince you that this is the case. And there are black holes also in these lower mass galaxies. On the other side, with the stellar mass black hole, there's also quite a lot of work to find them, because you can only indirectly find them. So either through binary systems or also gravitational wave detections. And there is also a lot of progress been made. There are many more gravitational wave black holes now. Also, Gaia was finding black holes astrometrically. And in the Milky Way, we expect many more stellar mass black holes. But it's also a lot of work to find those. But still, there is this observational gap of the intermediate mass black holes, and we want to understand whether those could be the seeds for the supermassive black hole. And so there are several seeding scenarios for the supermassive black holes. So either they form in the same way as the stellar mass black holes, and then they just merge and cross this gap really rapidly, or they collapse directly into a more massive black hole in the intermediate mass range, and then have a head start and actually grow very fast to the supermassive black hole case. And so this is the question, like which mass distribution do the original seed black holes have? And this is what I would like to understand. Okay, so what are the seeds of supermassive black holes? Okay, the different seeding scenarios will give us different predictions for the black hole distribution in the local universe. We have the direct collapse black holes, population 3 stars. These are the first stars. forming at very high masses, 100 solar masses or so in very low metallicity environments. And then we also have a third channel, which is the gravitational runaway. So in a star cluster, very dense star cluster early in the universe, you have very high densities. Those stars will get very close to each other and then merge to form very massive stars and go into black holes quickly. And in these dense environments, they can actually do runaway collisions and form into supermassive black holes rapidly. So these different seeding scenarios will give you different observables in the scaling relation. And one that I'm looking at is the black hole occupation fraction, or the fraction of black holes here as a function of galaxy mass. So you see that for all galaxy masses, you get, for the direct collapse model, you get very low fraction of low mass galaxy have a black hole, because in the merger process, you will then form the more massive black holes. And if you have too many massive black holes in the direct collapse case, they would overpredict the black hole mass galaxy mass relation here at the high mass end. So you see in the direct collapse, you have a over massive black holes in the low mass galaxy case. But yeah, these are the predictions actually for the different seeding scenarios. So you would form in for the population 3 stars, you have very many black holes at very low masses. And for the direct collapse, you have very few. And then you grow this to actually form your scaling relations as you go through the galaxy evolution process. So the predictions for the local universe, when you look at these different seeding scenarios, is actually telling you interesting things. So there are different models for the first star seeds, sorry. So you have the different groups give you different predictions, but they tend to be very high fraction of galaxies that have a black hole as a function of host galaxy mass, and all these masses are actually pretty low mass, so basically Milky Way and below. And the direct collapse seeding scenario, you have a very rapid rise of black holes, and actually at above 10 to the 10 solar masses, stellar mass of the host galaxy, all galaxies should have a black hole at the center. Okay, so this mass range in between around 10 to the 8 and 10 to the 10 solar masses, looking for black holes in those low mass galaxies is still one of the best ways to determine in the local universe what are the seeding scenarios for black holes in the early universe. Okay, so what is happening at the centers of these low mass galaxies? Do we find black holes there? Okay, so we've looked at the sample of basically bulgeless galaxies, but also dwarf ellipticals. And we looked at galaxies that host a nuclear star cluster at their center. So also the Milky Way hosts a nuclear star cluster. And it's actually interesting because we look at those because they have very high stellar densities. So if you have a black hole there, you would have many orbits of stars going very close to the black hole. So the dynamical imprint of the black hole, you can actually see it. Looking for the black hole in the Large Magellanic Cloud is very difficult because you do not have like a distinct nucleus to look for the black hole, so it's more difficult to find. Okay, but when we look at those, and you see here also the Milky Way is among those, they look similar but also a little different. These are the densest star clusters in the universe, and you may ask yourself, okay, are these typical galaxies, or is this a special thing to have a nuclear star cluster? And so in a recent review that we compiled with my close collaborator Anil Seth and Thorsten Brücke, we found that nuclear star clusters are almost ubiquitous in those low mass galaxies. And also Niels Hoyer, my current PhD student, he has actually looked at this relation in the local universe, so in the local volume, and also found the same thing, that not only in galaxy clusters, where this has been very well studied before, but also in the local volume out to 10 megaparsec, we find that in this mass range that is important to us, between around 10 to the 8 and 10 to the 10 solar masses, you have many galaxies actually, almost 80% of galaxies hosting a nuclear star cluster. So if we look for black holes in those, it's like looking at the typical galaxy. So it's not something very special. So that's what made us confident that our program could work and tell us something about the black hole occupation fraction. I told you that we looked at the Milky Way as if it was an external galaxy. It took us 2 nights of observing time and basically an entire PhD to finish this. But so we trust the models. And in the nearby galaxies, we can basically, with an IFU, like with Symphony or now Eris at the VLT, you have a field of view about 3 arcsecond on the side with adaptive optics for the spatial resolution we need. You can resolve the sphere of influence of these potential black holes. And so we find here a line of sight motion, the gas, but also here for the stars, you see that these rotate. And actually, they also show imprints of black holes. Here we only get an upper limit, but we're having this as our entire sample. So this is basically a complete sample out to 5 megaparsecs, where we have both ellipticals and spirals, and we're having the total stellar mass of the host galaxy in the range that I told you is important to us. And in all of those cases, we actually do find dynamical imprints for black holes. This is the upper limit case, but then also in 2 of those, we do not see any rise in the velocity dispersion or any sign for a black hole. We're still hopeful that we can do this better because there is quite a lot of shot noise actually in these observations. So maybe the black hole is just hiding there. But anyway, the data of the others were not good enough to do the measurement. So in 7 of the 9 hosts that we studied, we find a black hole at the center. And even if the ones that we couldn't study here in our complete sample, even if they have no black hole at all, the results, they're actually pretty constraining because more than 50% of the galaxies we looked at in this mass range, in this complete sample, they show a sign of a compact object at the center that is required to explain the dynamics. And so this is basically ruling out the direct collapse seeding scenario because we are at a very high fraction of local galaxies with the central black hole. So these constraints from our survey, they favor the first stars as the seeds in those low mass galaxies. Okay, so we have made quite a bit of progress here. So I showed you that this might be a detection threshold, and it actually is. So when we have the data to do this properly in the local universe, we actually find the black holes there. And we would need better telescopes to actually go further because you need the spatial resolution to look at these black holes. Okay, so in those low mass galaxies, the first star seeds seem to be favorable. And still, the question is, if the black holes form at these masses, and they then, somehow need to cross this gap, right? So will we be able to find the intermediate mass black holes? Maybe we would need to look in even lower mass galaxies or further away, whatever. But we need definitely better spatial resolution. So what we did was actually looking even closer than the 5 megaparsec sample. And one of the best examples is actually the Sagittarius dwarf galaxy that is sitting behind the galaxy, behind the bulge. And the nucleus of the Sagittarius dwarf is the globular cluster M54, which has been discovered before, like more than 200 years before the Sagittarius dwarf by Charles Messier. And here is a movie of how this whole thing has happened. I hope it plays. Once again, no. No. I tested it, it worked, but now, of course, it does not. So you see this, basically what should have happened now is that the Sagittarius dwarf starts here, wrapped around, no, it actually starts here, it's wrapped around the Milky Way kind of twice. It crossed the disk several times, 3 times, and every time it crossed the disk, it gives a burst of star formation in the nucleus of the galaxy. And so this is the amount of stars formed as a function of time, and you see these bursts of star formation when the material in the nucleus of the galaxy is compressed and then triggers star formation. And what we did, we looked at the M54, the nucleus of the Sagittarius dwarf, and it's been the work of my PhD student Maite Alfaro Coelho. We had 16 pointings with the MUSE integral field spectrograph, and this is a quasi-color image from the cube collapsed. So we have a spectrum at every position here, and we can then get the metallicity of the star, also the line of sight velocity. So we had more than 6,600 stellar spectra of the nucleus of the Sagittarius dwarf, M54, and we can reconstruct its formation history. This is the color magnitude diagram of M54, quite complex, color-coded by the signal-to-noise of our spectra. And now color-coded here in the top is the metallicity of the stars, and then when we infer from the metallicity an isochrone for the population, this is what you can zoom into the main sequence turnoff. It actually separates very well. The metallicity is here, and here the age. So you have an old population, and then the younger populations turning off later. So from these, we can actually reconstruct the formation history of M54 on a star-by-star basis, and we get an dominant old metal poor population, an intermediate age metal rich, and the young metal rich population. And if the movie would have shown kind of that this burst of star formation in the intermediate age is triggered by the first passage through the disk, and these bursts by the later passages. So it's connected with the history of the galaxy that fell into the Milky Way. And we can then test whether if we collapse the entire spectrum of all the 16 MUSE cubes and get one really high signal to noise integrated spectrum, whether we can reconstruct the same formation history and the age metallicity relation. And this is work by my PhD student Alina Böcker, and she showed that is very comparable. Also in the integrated light SSP models, you basically reconstruct these different bursts of star formation from the integrated spectrum, which is pretty cool. Okay, but we are interested in the black holes. This was just a sidetrack, but we can also do a lot more on using the spectra. But we wanted to look at the kinematics and see whether those will show us anything about the presence of a black hole in M54. So you see the stars, they also rotate. And the black hole would show up as an imprint in the increase in the velocity dispersion profile, but actually when you look at the profile, it drops at the center. And this is because the cluster is too crowded for our observation. So because we do the measurement on individual velocities and compare them and then get the dispersion of velocity, they're all going to the same mean velocity, and then the velocity dispersion drops. So this is just an observational artifact. And the imprint of the black hole would really be exactly where we are kind of blind because of the crowding. Okay, so what do? We need higher spatial resolution for sure to detect this black hole, but then we were lucky enough that MUSE was upgraded with adaptive optics. So this is our ground-based seeing limited cube, but then we got wide field mode AO cube, and then in the center, the narrow field mode, which in the wide field mode AO looks like that, but when we turn on the AO, this is what we get. So we get an increase of a factor 10 in spatial resolution, which is fantastic. We also get the increase in velocity dispersion, but then Maite went on to a faculty position and the paper is still not published, but we are hopeful that we can find the black hole. So we do think it's there, but yeah, it's not yet published. Okay, so this is what we can do with MUSE at the VLT, but with the next generation extremely large telescope, we can do even more because we get another factor of 10 spatial resolution. And so we then can constrain black holes of the order of 1,000 solar masses. But you may have seen the recent announcement of ESO that the start first light of the ELT is now expected to be in 2030. So we cannot wait that long. We need to do something else. So that's what we did was to define a project for an even closer galactic nucleus. So M54 is at the distance of 27, 28 kiloparsecs. So it's at the other side of the galaxy. But there is an even closer galactic nucleus to us, which is Omega Centauri. It's actually our closest galactic nucleus. It's even closer than our own galactic center, which is at 8 kiloparsec distance. And Omega Cen is at around 5.5. So a factor of 5 closer than M54. So we can do many more things and we can really gain a lot. It's the most massive globular cluster in the Milky Way. M54 is only the second most massive. And it's long been suspected to be the stripped off nucleus of a former galaxy that merged with the Milky Way very early on, so much earlier than the Sagittarius. So when you zoom in with the HST, you can see a lot of increase in spatial resolution. And so we put together a project called Omega Cat, where we looked at Omega Cen within the half-light radius. Here is the center by Anderson. And we have put together data set with the Hubble Space Telescope, so multi-filter and also proper motion. This is the work of Maximilian Heberle, who's just graduated last week. And then there is a coverage with a Muse spectroscopy with more than 100 fields. This has been the PhD work of Selina Nitschei. She graduated last summer. And so we have multi-filter and also proper motion measurements. This is the Omega Cat team. So many of them are in the room here. I'm very proud. This is really a fun project and a really great collaboration. So I'm co-leading this with Anil Seth. And as I said, Selina graduated last year. She was leading the Muse part. Max was leading the HST part. And Kelly Klons, who is a PhD student with Anil, that she's spending time here in Heidelberg at the MPIA, will graduate in May and is putting together both parts. And then also in the group, we have Peter Smith, who's doing the dynamical modeling, Stefano Sousa, who's actually doing the connection to the former host galaxy, and Ishan, who's a master's student looking at the most metal-rich population. So this is spectacular data that Max has compiled for his PhD. So Max has looked at more than 800 individual images taken with the HST, the Hubble Space Telescope, in basically two cameras, the ACS and Wide Field Camera 3. And this has been early images, but then Omega Cen was chosen as the calibration field for those cameras with the HST. So it's been revisited by the HST really regularly. And it's a data set for more than 20 years. And Max has done a heroic effort to actually look at all the individual positions of all the stars in those fields. We have added also a second epoch outer field, so we get multi-band images. And here is the color composite image that Max has put together. So this is spectacular data. And by comparing the positions of the stars in the consecutive images, Max could reconstruct the proper motions of those stars over more than 20 years. So these are proper motions for more than 1.4 million stars. And in those data, Max discovered 7 stars that are moving faster than the escape velocity of the cluster. So those stars should not actually be there, and they're all at the center of Omega Cen. So just going a little bit deeper into the data here, you see here the data color-coded with the time when it was taken. So you see here from 2002 to 2022. And yeah, the two different cameras, ACS and WIFC3. And here the color coding is the number of used epochs. So you see for some of those stars, we had more than 400 individual epochs. That gave us like a superb proper motion uncertainty of smaller than 7 micro arc seconds per year, which is 0.17 kilometers per second at the distance of Omega Cen. So this is superb data, and only those data set, actually this data set allowed the discovery of those fast stars that are overabundant at the center of Omega Cen. So there are some fast stars that are consistent with being just foreground or background stars in the Milky Way, but there is this cluster of stars very close to the center. the Anderson van der Marel center. And the centermost star is actually also the fastest star at a velocity of 113 kilometers per second. And this star can only be there because it's bound to a massive object at the center of Omega Cen. So this is quite a spectacular measurement. And really, I can tell you already at the beginning of my career, people were going back and forth whether Omega Cen hosts an intermediate mass black hole. And I think we've now actually found it, which is quite exciting. Okay, this is the trajectory of the fastest star, where you see the positions color-coded by the epoch of observation. So this is going on a straight trajectory. And this also tells you that it's not actually in a binary, because otherwise those would not be a straight trajectory. It would have a curvature. And over this time of the observations, we do not see any curvature. This is a test we did whether this could be actually explained by foreground or background stars. And it's very consistent with a model for the Milky Way. This is the fast star density as a function of projected distance from the center. And you see a Besançon model that actually predicts, okay, there are some fast stars, but this is really this overdensity towards the center that rules out just the chance detections of fast stars towards the center. And then we want to constrain the mass. And so there we need a model for the stellar distribution, for the escape velocity, which is pretty well measured at 62 kilometers per second. And you see the velocity of the stars, and this is only in two dimensions. So we measure the velocity in proper motion. And that's why these are actually lower limits, because you would have also a third dimension, the line of sight velocity, that would bring them to even higher velocity in 3D. And so this gives us a lower limit to hold on to all of those stars. Even the fastest one is the 8,200 solar masses. So this is really in the intermediate mass regime. And previous models have also predicted about 40,000 solar masses for the black hole. This is where the stars would be then. Okay, so just such a nice movie that I want to show it, because this is basically similar to the movie I'm showing at the beginning of the talks. When we zoom into the galactic center, now we zoom in to our closest galactic center, Omega Cen, where we're now switching from ground-based to the VST observations, and then also to Hubble. And then you can follow the motion of these individual stars that Max has measured, and identifying those fast-moving stars that are actually surprisingly faint. The fastest stars are some of the faintest stars, and that's why they have not been seen before, only in our deeper and better catalog. And this is now moving forward. It's basically moving into the future. You see, we have extrapolated on straight trajectories, but obviously we would like to measure a curvature at some point in the future. So let's see. We have a couple of programs lined up to do better measurements. But I told you we not only have the HST positions and proper motions and colors, but we also have spectra. And this is work that Selina Nitschai has led in her PhD. And when you look at the globular cluster, you often sort the stars by color, with the red stars on the right and blue stars on the left, and magnitude, so you get the color magnitude diagram. But remember, at every position here, for every dot, we have a spectrum. So we can measure the metallicity, and we can color the color magnitude diagram by metallicity. And you see that these different sequences, they separate out super well. So we can also measure the age metallicity relation. And this is work that Kelly has done, and I'm coming to it. So we also get the line of sight velocities. So you see the overall rotation of Omega Cen. So the red side going away from us, the blue side coming towards us. It's very low level rotation, but it's rotating. And in the MUSE narrow field mode observations, we detected a counter-rotating core in Omega Cen. So the overall rotation is here. But then when you zoom into the central 40 by 40 arc seconds, you see this side is red basically, but it's actually counter-rotating with in the very center. And here, I don't know whether you see it from the back, but this is the Anderson van der Marel Center. This is the kinematic center taken into account this counter rotation. And here you have the velocity, the line of sight velocity map, and this is the velocity dispersion map. And here is the peak in velocity dispersion. This is where Eva Noyola in 2010 measured a very high black hole mass because she actually took this dispersion peak into account and got 40,000 solar masses. So also this counter rotation and having these news data kind of resolve a long conflict in all of this back and forth. So we have also follow-up observations of our fast-moving stars with the nearest spectrograph, and we've put in another MUSE proposal to also get the line of sight velocities, but I showed you these are very faint stars, so it's a pretty hard measurement to make. Okay, I told you Callie Clance is working on deriving the ages, so she's combining the metallicities from Selena's work with the photometry from Max's work, and with new isochrones with that include the helium enhancement, also C plus N plus O abundance variations. And so she could measure the age metallicity relation for the subgiant branch stars, and seeing that omega Cen has actually a pretty complex age metallicity relation. So you have this part that is consistent with the what we suspect is the former host, the Gaia sausage enceladus dwarf galaxy. And we have this kind of in situ self-enriched population, but we're kind of trying to figure out how this all forms, but we have the best data set now to do it. Okay, that's what I kind of alluded to, that probably the former host galaxy of omega Cen has been the Gaia sausage enceladus galaxy. So when you then look at the black hole mass versus velocity dispersion, this is more or less the region where you would put omega Cen or Gaia sausage enceladus, and this is Max's IMDH constraint, and it kind of falls pretty well onto the scaling relation for the black holes in galaxies. Okay, so we are still working on this and also want to connect the chemistry of the former host. This is what Stefano is working on, and as I said, Peter will do the more advanced dynamical modeling with you, hopefully using discrete Schwarzschild models in the future. Okay, so this brings me to the end of my talk, which I hope you enjoyed. So I hope to have convinced you that we made quite a bit of progress on the detection of black holes in the low mass regime here. So we pushed the low mass limit by an order of magnitude and got the first complete sample in the very local universe. We then, with this, start to constrain the seed masses of the supermassive black holes. There was this big question mark whether intermediate mass black holes exist, and I think with omega Cen we have now the best candidate. We want to definitely follow this up. And we have now the means to do this because with MUSE we are doing pretty well, and we can also look at a few more examples. With JWST, this is what I told you, we have already 2 programs approved, one for the near spec when we measure the line of sight velocities, but also with near chem where we want to do more accurate multi-cycle proper motion. Hopefully getting the curvature and the acceleration of the star. And with the ELT, we can do even better because Mikado will have an even better spatial resolution, and also with Harmony later on, we can do more targets and really constrain whether also lower mass globular clusters also host intermediate mass black holes. And it's important to characterize those systems because those will be the prime targets, the intermediate mass black holes and the mergers of those for the LISA-spaced interferometer that will detect gravitational waves from these sources. So I think black hole research really has a bright future. And I would like to thank my group and also the funding sources for actually making all this possible. So this is the current group, but also my previous PhD students and also the rest of the collaboration. Thank you very much.
Standing ovations. Good. We open the floor for questions, particularly if there are students and postdocs that have questions. Everything was perfectly clear. Volunteer.
Thanks for sharing this amazing data and results. I was very interested that the black hole occupation fraction in the local universe is basically ruling out the direct collapse scenario for black hole seeds. Especially since black hole seeding has also been a hot topic in the JWST era, with many papers claiming overmassive black holes at high redshift, even though they are affected by large uncertainties and selection effects. Yeah, I was just curious, what is your impression? Are your results inconsistent with some of these claims? Do you think there's a way to reconcile them?
Yeah, so I think you mentioned one of those already, is like the selection effect. I think the black holes at the highest redshift, I think we're basically targeting the most extreme environments with detecting those quasars at the highest redshift. And I think in some parts of the universe, the direct collapse could actually happen, or actually like a very rapid growth of the black holes, because you would need to make them grow to masses of 1 billion solar masses very rapidly. But I think especially the runaway gravitational collisions could be a good way to reconcile the two channels, basically, because you would go through a quasi-stellar phase for all black holes, and just depending on the environment you're in, with all the materials that you have, you could either stay in, because I was looking at very low mass galaxies it's also a very special environment in the universe, right? Where these things are happily staying at those low masses. So it's very quiet in those neighborhoods. While in the highest redshift quasars, you probably are in the filaments of the dark matter halos, and those are the most massive regions. So I think it really depends on the environment, how quickly you then grow the black hole. Yeah.
More questions.
Michaela has a question.
In the bottom corner, you're hiding.
Thank you, Nadine, for these amazing results and overview. I have also a question that is along this line. Actually, I have two maybe, but let me start with one. So how well can we reconstruct the history of the host of Omega Centauri based on the data that we have now? And what can we learn from this in terms of the evolutionary scenario for the star cluster and the possible black hole?
Okay, so I think the best observation so far has been okay, there are several lines of observation. So first of all, there is Omega Cen, and also has a tidal stream, basically, and we're trying now with Stefano to connect the tidal stream to also the globular clusters, and potentially you could also connect it to some stars you find in Gaia. But it's difficult, actually, because the merger happened a long time ago, and that's why it's basically, dispersed in the Milky Way. The globular clusters can maybe tell you the best story, or give you the best hints, and so that's also been in this slide has been here. So this line here is basically the age metallicity relation that is linked to the globular clusters of Gaia, Sausage, and Enceladus. And yeah, and from that, also the number of globular clusters, but yeah, the metallicity, you can reconstruct the possible mass of this former host. But we would like to do a little better also with chemical evolution models to then, also with abundances. So here, Kelly, I should mention this, she just came back from Paranal. She had written a flames proposal for stars, basically on these two different branches here. So we can measure actually abundances for those different stars that can tell us something about the formation history of the stars. And yeah, so we can get a better idea of how and when the stars formed and whether they're part of the old globular cluster that formed the center of Omega Cen, or the enriched star formation later on. And yeah, kind of, there's still a lot of question marks. And it's definitely not your regular globular cluster you have there, because it's really was sitting at the center of a galaxy before. That's why it's so complex also with the several population. We're working on it, but yeah.
Nadine, I wanted to ask you on the question of when do black holes actually get to the centers of galaxies, and perhaps something, what can be said speculatively about the transition from the stellar mass to the intermediate mass black hole regime? How much accretion versus merging, and was it just one black hole that happened to sit still at the center of the initial galaxy that then became the seed? Or how should I think about this?
Yeah, it's a question. And obviously Omega Cen is also a good target for this, because the accretion stopped when the galaxy fell into the Milky Way and stripped away the gas that would have maybe been the material to then grow further from. And so we are looking at a black hole that has been basically frozen in time at the, say, 9 billion years ago or so. So already at that time, it had a mass of above 8,000 solar masses. And so I think the likely formation happens pretty early, when the density of the cluster is very high. This is when the runaway collisions are most favorably done, basically early on. And then it can go through the phase of a very massive star that is actually very hot and is burning, you know, yeah, it's actually extreme conditions that could, in addition, explain all the peculiar abundance variations that you see in globular clusters. So I think we could solve two things at the time, but we're still trying to figure out how this works. And because globular clusters are the oldest systems that we see, and maybe in the most massive cases, you could have black hole formation very early on already. So I think to answer your question of when it happens, I think it would happen most likely early on in the formation of these dense stellar systems. Yeah.
Questions? Richard, are there any questions?
So do different scenarios make different predictions for the spins of the black holes? And could you test that by looking at mergers, for instance, that you might see in gravitational wave detectors?
Yeah, that's a good question. I think with the spins, you know, the gravitational wave detections could actually give you maybe the most, the best insight there. But then also it's difficult, because then the gravitational wave, the mergers, you could also eject black holes from the centers of those clusters. So that is another way to remove black holes from lower potential wells. So far, we have not been concerned with measuring spins in our galactic centers, because it's very difficult measurement to make. But maybe with LISA, this is something that one could start doing. But I really don't know how the LISA signals for intermediate mass black holes or extreme mass ratio spiral in spirals would actually look, depending on the spin of the black holes. Maybe Michaela would know that. I don't know. Yeah.
More questions?
I will not answer about the spins, but I just wanted to comment that also the masses are very important, because this is related to my question about how well we can reconstruct the history of the progenitor. And it's exactly connected with the kicks that can eject the seed during a merger. You can probably roughly try to have an estimate of what is the initial mass of the seed, if you can probabilistically study what mass the seed should have had to statistically prevent the ejection from the cluster. So even before then looking at the spin, that is a painful measurement and we need to wait for 10 years. Maybe one can try to cross-match the information and try to use that to reverse engineering the most likely seed mass. But yeah, since I have already the mic, maybe someone else. Yeah, I wanted to ask you about the models again, because the models are quite a moving target, unfortunately. So you compare the direct collapse and the top 3 seeds. But now there are many more nuanced and intermediate models in a sense. So do you think that the building blocks that started everything were more like a traditional POP3? Or you think that a POP2 like evolutionary scenario with a cluster of like normal stars could have done it?
Yeah, that's a very good question. I think it could also be, you know, because we're looking here at the globular cluster, and these are basically POP2 stars, so it's not POP3. Maybe there is a POP3 dark remnant underneath, and then the cluster has formed around it. That's possible, but I think it actually can also already work also with the POP2, but in extremely dense clusters. So, but I don't know, and I think so. Nobody knows so far. It's interesting for sure.
I see no further hands. Good. Then let's thank Nadine again.
Thank you.